Hello. In previous videos, I have discussed the sample mean, which is computed using the expression shown on this slide. I have explained that because this quantity is computed by adding together identical random variables, it is itself a random variable. I have further shown that the expectation of the sample mean is equal to the expectation of the identical random variables from which it was computed. Similarly, I've also shown that if all the random variables are independent, we can write the following expression for the variance of the sample mean in terms of the variance of x, which is here called sigma squared. I mention all this here because the aim in this video is to determine if we can derive similar expressions for the expectation and variance of the weighted mean that is calculated using the expression on this slide. In this video, we will assume that the xi are all identical random variables. In addition, we will also assume that all the wi are also identical random variables. These wi random variables will not be equal to the identical to the xi random variables. We will also not assume that the wi and xi random variables are independent. To be clear, however, every pair of wi random variables are both independent and identical. Similarly, every pair of xi random variables are also identical and independent. The weighted mean that is computed using the formula on this slide is computed by adding together random variables, so it is also a random variable. The aim of this video is thus to determine the expectation and variance for the weighted mean. To solve this problem, it is useful to solve a broader class of problems. Rather than trying to work out the expectation of the weighted mean, we will try to derive an expression for the expectation of any function of some random variables, as shown here. To calculate this expectation of f, we will rewrite the function f in terms of its Taylor series around the point where all the random variables that f is computed from are equal to their expectations. We will thus introduce the symbols μw and μx to represent the expectation of wi and xi, respectively. The Taylor series expansion of f around the expectation is thus the following. Notice that in writing the Taylor series here, we have truncated at first order. Furthermore, as we have written the function in terms of its Taylor series, we now have a linear combination of terms. We can thus exploit the linearity of the expectation operator as follows. Now recall that the μw and μx are the expectations of w and x respectively. This is important as it ensures that all these first order terms are 0. If we are thus willing to truncate the Taylor series at first order, we find that the expectation of the function is approximately equal to the value of the function f evaluated at the point where all the random variables are equal to μw or μx, their expectations. To make this clear, let's apply it to our weighted average. The approximation tells us that each of the random variables in the sum should just be replaced by its expectation, as follows. Every term in the sum is identical, so these are easily calculated as follows. The factors of n μw in the numerator and the denominator then cancel, and we find that the expectation for the weighted average is approximately equal to the expectation of the random variable x. To summarize this first part then, we have found that the expectation of the weighted average is approximately equal to the expectation of one of the random variables x from which it was computed, as shown here. This is the same result that we arrived at when we considered a weighted average that was computed with weights that were not random. The difference here, however, is that this relationship is exact when the weights are not random. If the weights are random, however, it is an approximation. Now that we've worked out the expectation of the weighted average, let's turn to the variance. Just as we did for the expectation, we will start by considering the more general problem of the variance of a function of some set of random variables, as shown at the top of this slide. To solve this problem, we will start by using the approximation that we just derived, namely that the expectation of f is approximately equal to the value of f evaluated at a point where all the random variables are equal to their respective expectations, as shown here. Next, we use the Taylor series to write an expansion for f around the point where all the random variables are equal to their expectations. As we did in the derivation for the expectation, we're going to truncate the Taylor series and write out only the first order terms. Now notice that these two terms cancel, and we are just left to multiply out the bracket. When we complete this process, we arrive at the following expression. Furthermore, to be clear, we only included the first order terms in the Taylor series when we multiplied out the brackets. The squares in this expression come because we squared the Taylor series, a Taylor series which, and to be really clear, only ever included first order terms. Let's now use the expression we just derived for the variance of the function of the random variables to calculate the variance of the weighted mean that is defined in this expression. For simplicity's sake, we will set the yi in this expression equal to wi xi. Our first task is thus to determine the derivative of the weighted average with respect to wj xj. This is a straightforward piece of differentiation and gives the result shown here. We next differentiate with respect to the wi's that appear in the sum in the denominator. This again is not particularly difficult partial derivative to compute and is shown here. It is worth noting, furthermore, that if we remember how the weighted average is defined, we can rewrite this derivative in terms of the weighted average as follows. We now insert these expressions for the derivatives into the equation at the top of the slide and arrive at the following expression for the variance of the weighted average. If we can replace the expectation of wx here with the weighted average, as the expectation for wx will be approximately equal to the weighted average. If you then multiply out all of the brackets, many terms cancel. I will leave this as an exercise and simply note that once the dust settles, you are left with the following result. To summarize this video, then, notice that the expectation of the weighted average shown at the top of this slide is approximately equal to the expectation of x. More importantly, though, we can estimate the variance of the weighted average by using the expression that has just appeared on this slide. Consequently, if we estimate a weighted average by sampling, we can use this estimator for the variance of the weighted average, and this will give us the error bar on our result. I am nearly finished, but I just want to finish with one word of caution. Notice that when we expand the square in the sum, in our expression for the variance, we get the following. If the averages were not weighted, the cross term here would reduce to the mean squared. The same thing does not happen here, however. There is thus no way that we can write an expression for the variance that is similar to our old friend, the expectation of x squared minus the expectation of x all squared. When we calculate the estimator for the variance of the weighted average that is shown on this slide, we thus need to first estimate the weighted mean. Only once we have done that can we then use the expression that is now shown in the box to compute the variance of the weighted mean. I hope this has helped you understand the process of calculating these errors. Thanks for your attention and good luck with your simulations.